mainly जो होता है, it is all about the efficiency of packing, definitely, and this is definitely determined by the relative interaction between the particle, no doubt. The fundamental reason is the interaction between the particle, right? Do you agree with me? The fundamental reason for the packing will be all about the interaction and also the type of particle. एक तरह के पार्टिकल हैं तो एक पर्टिकुलर टाइप का इंटरेक्शन होगा, अलग अलग टाइप के पार्टिकल हैं जैसे सोडियम और क्लोराइड है तो अलग टाइप का इंटरेक्शन होगा. तो टाइप ऑफ पार्टिकल, देयर साइज एंड रिलेट एंड द इंटरेक्शन बिटवीन देम. व्हेन आई से इंटरेक्शन मीन्स द अट्रैक्टिव फोर्सेस. तो कितना अच्छे से ये एक दूसरे को पैक कर रहे हैं, ये साइज पे भी डिपेंड करता है और इंटरेक्शन पे. ठीक है, तो ये जो पैकिंग है, इट इज़ अ वेरी इंपॉर्टेंट फैक्टर टू बी क्वांटिफाइड and it helps us to understand many things about crystalline solid, because when we discuss the properties, for example density, simple example, so कितना volume इस unit cell का occupied है by lattice point, that is called packing efficiency. So the formula is very simple. You have the volume occupied by the atomic sphere per unit cell. Okay, you have to keep this in mind, not randomly, per unit cell. अब वो किस पे डिपेंड करता है? This depends upon type of unit cell, naturally. So the volume occupied in this kind of lattice, which is the simplest case that we are considering first, simple cubic lattice, तो इसके अंदर number of atoms जो है 1 है per unit cell. ठीक है, per unit cell. Okay, so this is known. How much will be the volume? Suppose if I say, suppose radius of lattice motif, you remember motif जो आइडिया था, या आप कह लीजिए कि एटम, और even call it as sphere, is let's say r. ठीक है, तो इसकी जो अगर हम रेडियस की बात करें, सपोज हम कह दें कि इसकी जो रेडियस है वो r है, तो यहाँ से सेंटर से लगा के यहाँ तक का जो डिस्टेंस है लेट्स से r है, एंड इज गोइंग टू बी सेम फॉर all the atoms, right? This is r. So this is going to be same for all. Okay, so this is one parameter. Therefore the volume of lattice motif will be 4/3 pi r cube, assuming that they all are sphere right now. So if the radius is r for each sphere, the volume is going to be 4/3 pi r cube. Again, packing efficiency means Pe, and volume occupied by atomic sphere. So let's say V atom, okay, Va divided by V unit cell, Vu. Okay, Va means atomic sphere, and then Vu is the volume of the unit cell, and multiplied by 100%. So therefore for us here, Va in this case will be 1, because we know there is only one atom per unit cell, and that will be 1 into 4/3 pi r cube. So that is fine. And then what about the volume of unit cell? So unit cell volume is always very simple, because we are using the term called simple cubic lattice. सो क्यूबिकल लेटिस मतलब क्या? क्यूबिक लेटिस का मतलब क्या हो? इसकी सारी लेंथ जो है वो समान है. तो सारी लेंथ जो समान है, तो अगर एक लेंथ की लंबाई अगर a है, तो सारी जो लेंथ है उन सभी की लंबाई भी a ही होने वाली है. Vu that will be a cube. ठीक है, a into a. This is going to be the volume of the unit cell. But then we have two different parameters. One is the length of the unit cell a, and another is the radius. So radius of the sphere can be known easily. See, हमें कोई यूनिट सेल तो क्या एक फ्रेम है, बट आपका सब्सटेंस क्या है पूरे क्रिस्टल के अंदर? सब्सटेंस तो यही है ना. यूनिट सेल तो हमारा फ्रेम है. तो ये तो फिजिकली तो कोई एग्जिस्टेंस इसका होता नहीं है. ठीक है, फिजिकली एग्जिस्टेंस किसका होता है? आपके स्फीयर्स का. ये वाले जो एटम है, अगर आप उसको कहते हो, तो इनका स्फीयर का एग्जिस्टेंस होता है. इसका मतलब क्या हुआ कि आपकी रिस्पॉन्सिबिलिटी बन जाती है टू डिफाइन दिस लेंथ, which is like a frame of this unit cell in terms of r, because you can establish that relation very easily. Okay, you can see that this 1a is nothing but 2r. You can see this because the distance from center to center of the two atom is like r plus r. This is one r and this is another r. So one corner to another corner of the unit cell, if you go across the edge, the distance is going to be 2r. Okay, this is also r. ठीक है, ये यहाँ से गायब हो गया. So I hope this is clear. Why we are doing this? Because we want to eliminate the unknown parameter and then establish them in terms of known parameter. So I can say that a can be written down as 2r, and therefore this becomes 8 into r cube, and therefore packing efficiency for this simple cubic lattice, we are calculating first for the simplest cubic lattice, and that will be 4 by 3 pi r cube divided by 8 into r cube. If you solve this, of course multiplied by 100%, if you solve this, it will turn out to be 52.36%. What it means is the volume really occupied by the hard sphere per unit cell is only about 52% compared to the volume that you will otherwise imagine for a unit cell as a frame itself, you know. So अगर ये वाला जो वॉल्यूम है, इसको अगर आप 100% मानते हो जो यूनिट सेल का वॉल्यूम है, तो ये कितना वॉल्यूम है? ये है केवल 52.36%. Okay, that's what it means. So the packing efficiency in simple cubic lattice is this much. We will see at the end of the day when we compare this volume, the packing efficiency in various type of lattice, that which kind of packing will have the best packing efficiency. Okay, that's the idea. Any them also. So simple cubic is the simplest one, where we found out the packing efficiency is 52.36%. So the next one is HCP or FCP. That is the one which we have dealt with the most, okay, in understanding. ठीक है ना, आपने देखा था हेक्सागोनल क्लोज पैकिंग स्ट्रक्चर, उसको कैसे विजुलाइज, और उसी का दूसरा तरीका होता है विजुलाइजेशन का, उसी लेटिस सिस्टम का, वो है फेस सेंटर्ड क्यूब, ओके, और क्यूबिक क्लोज पैकिंग, either of the two. So in this kind of lattice arrangement, you already know that number of atoms per unit cell, number of spheres per unit cell are 4. if you remember, ये चीज पता है आपको, हमने कैलकुलेट की थी, इसमें नंबर ऑफ स्फीयर्स पर यूनिट सेल हमारे आते हैं 4. So we will be using, right, like here we found out the number of unit cell per unit, number of sphere per unit cell was only 1. Okay, we calculated. Now it is easy to find out how much is the volume that only the spheres will occupy per unit cell. ठीक है, just like here. So again we will apply the same formula. VA here is going to be 4 into 4 by 3 pi r cube, right? Because अगर हर एक स्फीयर जो है इसकी रेडियस फिर से r है, अगर हम इमेजिन करें उसी तरह से जैसे प्रीवियस केस में किया था. So suppose radius of each sphere is r, therefore VA, that means the volume occupied by number of spheres per unit cell. एक यूनिट सेल को अगर आप देखते हैं तो टोटल वॉल्यूम ऑक्यूपाइड बाय ऑल द स्फीयर्स पर यूनिट सेल, per unit cell in the lattice or in the crystal will be 4, because there are 4 spheres per unit cell, into 4 by 3 pi r cube. This is the volume of only one sphere and there are 4 of them, so this is going to be the volume of just the sphere in a unit cell. So this is one thing. Then VU, your starting point can be always which is a cube, correct? Because anyway we are even in this case we have already said that we are taking a cubical lattice, and in the cubical lattice there are 6 face centered lattice point also. ये क्यूबिकल है, इसके अंदर भी तो क्यूबिकल है, मतलब इसमें भी हर एक लेंथ जो है वो a ही होने वाला है, ये भी a है, ये भी a है और ये भी है. तो इसका primarily if you have to just write down the volume in terms of unit cell length, that is going to be a cube. But now we have to convert this a in terms of r, which is known parameter, है ना. तो अब उसके लिए क्या कर सकते हैं, हम इसकी थोड़ा सा क्लोज एग्जामिनेशन करते हैं इसको, ठीक है, और देखते हैं कि इसमें जो स्फीयर है वो कैसे अरेंज है. बिकॉज यहाँ पे आसान था. देखो अगर ये दो स्फीयर आपके कॉर्नर पे एक दूसरे को टच कर रहे हैं तो आप स्ट्रेट लिख सकते हैं a इज इक्वल टू 2r, नो डाउट. बट एक्चुअली स्पीकिंग दूसरी ज्योमेट्री में ऐसा नहीं होता, दूसरे लेटेस्ट अरेंजमेंट में ऐसा नहीं होता। उसका रीज़न बता रहे हैं। आप अगर समान जो रेडियस वाले अगर स्फीयर हैं और उनको आप इस तरह से जब अरेंज करते हो, ये तो यहाँ पे हमने डिस्टेंस पे बता दिया है, पर आपको अगर ये बिल्कुल पास में है एक दूसरे से सटे हुए, तो ये जो फेस है ना, यहाँ पे आप देख सकते हो जहाँ पे 1 2 3 4, ये अगर आप प्राइमरीली 1 2 3 and 4, I am considering this plane, and then there is a center, face center. This is like a central one, let's say X. Okay, this atom is at the face, this one, then this one at the top, this one behind this one, and then there is one here, there is one here, there is one here. Okay, so 1 2 3 4 5 6, these are on the faces and these are at the corner. So if you look at this one, I said that when you try to put them together, 1 2 3 4 and the 5 of one plane together, then you will actually end up creating a certain separation between the corner atom. They will be touching directly across the diagonal of the plane. Okay, diagonal of this plane they will be touching, no doubt. But then this touching, because this is in touch with all these four, this will try to, like, push all the four little bit away from each other, because the geometry is sphere, and ये जो थोड़ा सा गैप हो जाएगा, ये आपस में कभी भी टच नहीं करेंगे। इसका मतलब क्या हुआ, डायरेक्ट टच किसका होगा, केवल ये जो कॉर्नर पे दो एटम होंगे और ये बीच वाले का। उसी तरह से इस तरफ से भी वैसा ही होगा अगर इस डायगोनल में जाते हो तो। लेकिन ये जो साइड वाले जो हैं ये आपस में टच नहीं करेंगे। तो इसमें आप ये नहीं कह सकते हो डायरेक्टली कि A इज इक्वल टू 2R, यू कैन नॉट से दैट। डू यू एग्री विथ मी? Right now you can see that the geometry doesn't allow you to simply put A is equal to 2R, which was very simple in this case, because you don't have anything in the center, there is only void here. But now in the void you are trying to put something which is of the same size as this sphere, so it will tend to push all these sphere a little bit away from each other, and that's why you will have a certain gap in between. So here your job is now to find out this A in terms of R here across this length, which is easy, not very difficult, let me tell you. So what you have to do is you have to first just look at this geometry of this cube first, and then you can divide this geometry into two half, and now you have this like right angle triangle here, and you can apply Pythagoras law, because this length is A, this length is A, and here from here to here this will be, suppose this sphere will have the total size here 2R from here to here. The whole of this length can be divided in terms of R, which is easy. Suppose if I go from point 1 to point 2 to point 3, these junctions actually, okay, 1 2 and 3, 1 2 3, and then reach this fourth point. You see that what's happening is you can define these distances from point to point in terms of R, because this is R, this is 2R, and this is R. So basically the total AC, the value of AC in this in this triangular right angle triangle is 4R. Okay, now this AC square can be written down as AB square plus BC square. So that is equal to A square plus A square, right? So 4R square is equal to, which is like square of this 4R, and then A square plus A square. So you can very easily say that therefore R is equal to, if you sort this out, because here you have 2A square first, and then if you take the square root of this, it will be A into root 2 divided by 4, that is equal to R. So the R value you have established, or you can say that if you can say that in terms, A value in terms of R is 4R divided by root 2. Okay, so I have actually done. So this A cube, and that means 4R divided by root 2 cube. If you divide this one by this one, okay, everything will turn out to be very simple. Therefore packing efficiency, which is nothing but VA upon VU, and that will be, if you do all this thing calculation, of course there is a multiplication by 100, I am always forward. and if you do the calculation, this will turn out to be 74%, which is the number that I have mentioned at. Okay, then there is another type of lattice system which is called BCC, body centered cube. बॉडी सेंटर्ड क्यूब के अंदर जो है कॉर्नर पे तो वही 8 एटम आपने इस तरह से इमेजिन कर रखे हैं लाइक सिंपल क्यूब, बट इनसाइड द सेंटर ऑफ दिस क्यूब अगेन यू हैव टू इमेजिन one more atom, or let's say the sphere. So this becomes like a body centered cube. This kind of arrangement is also found in many lattice system. Well, so if that is so, how do you find out the packing efficiency for this? So the first thing first, you have to know the number of atoms per unit cell in BCC, and that is 2, because आपको पता है कि इनका कंट्रीब्यूशन 1 होता है पर यूनिट सेल, एंड दिस इज एक्सक्लूसिवली जस्ट द पार्ट ऑफ दिस यूनिट सेल, बिकॉज ये बीच में है तो ये किसको कोई और यूनिट सेल शेयर ही नहीं कर सकता, तो ये जो है ना इन सब से घिरा हुआ है, तो ये केवल इसी का है, तो 1 + 1 1 फ्रॉम ऑल दिस 8 एंड 1 फ्रॉम दिस, सो देर आर टोटल ऑफ 2 atoms per unit cell in BCC. Okay, having known this, now the next part is let's go with this again. Let me show you in the similar manner. So therefore VA, that means the volume occupied by all the spheres per unit cell of this type, is 2 into 4/3 pi r cube, assuming that the radius of each sphere is again r. So this is simple, है ना. अब v u and हमको फाइंड आउट करना है, जो हमने शुरुआत में ही कह दिया कि वो a क्यूब है. इन टर्म्स ऑफ लेंथ पैरामीटर इट इज डेफिनेटली a क्यूब, बिकॉज ऑल दीज आर्म्स, the length, width and the height, they are same and they all are a. So this is a modeling parameter, this is not an experimental parameter. This you have to find out, and you are able to find out this only in terms of radius of the sphere, है ना. तो आपको पहले रेडियस ऑफ द स्फीयर के टर्म में इसको a को एस्टैब्लिश करना पड़ेगा, और फिर बाद में आप जो पैकिंग एफिशिएंसी है जिसका फॉर्मूला ये हम यूज़ कर रहे हैं VA/VU इंटू %, तो पहले तो आप जो है इसको a क्यूब को r के टर्म में एस्टैब्लिश कीजिए. तो हम वही मेथड इस्तेमाल करेंगे यहाँ पे भी, लेकिन ज्योमेट्री को इसको अगर आप ध्यान देखें, देखिए इसमें तो बहुत सिंपल था, इसमें एक ही प्लेन के अंदर ही हमने ये सारे के सारे एटम की अरेंजमेंट को इमेजिन कर लिया था. ये अगर किसी भी एक भी फेज को आप अगर पिकअप कर लें तो आपको सारी स्टोरी यहाँ पे ख़त्म हो जाती है, क्योंकि जो एटम है पूरे प्लेन में कहीं ना कहीं तो एक दूसरे से टच है ना, एक ही प्लेन में, और उसी प्लेन में आपकी ये जो 2 लेंथ हैं a हैं, तो इनके और इसके बीच का रिलेशन बहुत आसान है. लेकिन BCC के केस में आपका जो एटम जो कि हर एक दूसरे कॉर्नर एटम के टच में है, ठीक है, वो कहाँ पे है, सेंटर में है, वो प्लेन में नहीं है. जैसे मैंने ये यहाँ पे ज्योमेट्री में बताने की कोशिश की है, इस बॉक्स को आप अगर आप इमेजिन करें तो ये जो बीच का स्फीयर है यहाँ पे दिख रहा होगा आपको, ये एक्चुअली में क्यूब के सेंटर में है, ठीक है, और ये जो कोने वाला हिस्सा है ये एक स्फीयर का है यहाँ पे इस कोने में, यहाँ पे ये दूसरा कोने में एक स्फीयर है, और ये जो 2 कोने में के स्फीयर जो हैं ये सेंटर वाले स्फीयर के इस तरह से टच में है. एक्चुअली में उसी तरह से हर कोने का स्फीयर इसी तरह से टच में, बट ऐसा करने से होता क्या है, जैसे मैंने पिछले केस में हमने बताया था कि यहाँ पे जो गैप हो जाता है, जो साइड वाले जो स्फीयर होते हैं कॉर्नर वाले, उनके बीच में गैप हो जाता है, तो यहाँ पे भी वैसा ही होना है. हालांकि मैंने यहाँ पे दूसरे कॉर्नर वाले स्फीयर को क्लैरिटी के लिए दिखाया नहीं है, बट आप समझ सकते हैं कि अगर आप यहाँ पे दूसरा स्फीयर रखेंगे जो इसका कुछ हिस्सा क्यूब का ऑक्यूपाई करेगा, तो इनके बीच में गैप होगा, इसके बीच में कॉर्नर वालों के बीच में गैप हो जाएगा, ठीक है. दे विल नॉट बी टचिंग डायरेक्ट. थोड़ा सा इसको ध्यान दें तो कुछ इस तरह का दिखाई देगा. ये क्यूब है, और प्लेन में जो अगर आप देखते हैं तो ये इंटरनल स्फीयर है, ये बाहर के एक प्लेन में, जैसे 1 2 3 4, तो ये 1 2, अगर मैं इसको 1 कह दूँ, 2 3 एंड 4, और ये आपका जो है सेंटर वाला है, सेंटर का. तो ये जो है ये सेंटर का एटम है, जो आप इस प्लेन की तरफ से देखें, ये पहला एटम है, दूसरा एटम है, तीसरा एटम है और फोर्थ एटम है. तो ये जो एटम सेंटर वाला जो है वो भी इनको टच कर रहा है सबको, इसीलिए थोड़े से ये भी बल्ज्ड आउट है. अच्छा, इसमें जो बल्जिंग आउट होगी, ये जो गैप है, नेचुरली ये इतना नहीं होगा जितना कि आप इसमें विजुलाइज करेंगे, बिकॉज यहाँ पे डायरेक्टली ये फेस में जो टच करेगा तो ज़्यादा बल्ज करेगा। अच्छा, ये यहाँ पे थोड़ा सा अंदर की तरफ पुश्ड है, इसलिए थोड़ा सा कम गैप हो जाएगा, बट डेफिनेटली गैप होगा। तो इसका मतलब क्या हुआ, इस केस में भी आप डायरेक्टली ये नहीं कह सकते हो कि A इज इक्वल टू 2R, बिकॉज देर इज एन एक्स्ट्रा गैप हियर, बिकॉज दिस इज R, बट देर इज अ गैप विच यू डू नॉट नो. So you cannot say again even here A is equal to 2R. That's a problem. Okay, but then it is very easy again to make use of the geometry and then be able to establish the relation between A and R. So what do you do then? देखो, ये डायगोनल है सेंटर में, ये जो है ना क्यूब का, इसमें ये डायगोनल AD. Okay, from this corner of the cube to this corner of the cube, this is front cube, this is this is front point and this is the back side point, front down back side up. ठीक है, तो ये जो है ये डायगोनल जो है इसमें से जा रहा है. अच्छा, अब ये वही बात आ जाती है कि यहाँ से ये डायगोनल के अक्रॉस भी अगर आप जाते हो तो जहाँ जहाँ पे ये स्फीयर एक दूसरे को टच करेंगे वहाँ तक का आपको ये डिस्टेंस पता है. ये R है, फिर से उसी डिस्टेंस ट्रैवल करना है, वो आपको अक्रॉस 2R ट्रैवल करना है डायगोनल में. ठीक है ना, मतलब अक्रॉस 2R मीन्स along the whole of this complete sphere. Then again there is an encounter of R. So basically the length of AD is 4R. The length of AD in the whole of this, we know that it is 4R. This is one thing. Fine. Then what do you do with this? Okay. Now if you want to make use of this R, which is known in terms of diagonal, somehow you should be able to establish the relation between this and then the side of this and then one of the diagonal in the plane. See, this diagonal is across the center of the cube, okay, but this diagonal is on the plane. On the plane we know it is directly related to both arms, right? But then this is not directly related to both arms. This is related to one arm A, but then another diagonal in the plane DB. Think about this. DB is in the lower plane. Okay, DB is just like in the lower plane, and this length is across one of the edge, which is A. So you do not know, let's say DB. Acha, why we are interested in finding out DB? That means from the diagonal across the center of the cube, okay, the diagonal which is running across the center of the cube, I want to find out a diagonal which is on the plane of the cube, one of the plane of the cube, because this is the direct related with the two arms, just like previous case. तो हम क्या करते हैं, यहाँ पे दो दफ़े पाइथागोरस अप्लाई करते हैं. पहली दफ़े में हम केवल इस ट्राइंगल को इमेजिन करते हैं ABD. ओके, ABD. ओके, डजेंट मैटर, मैंने यहाँ पे ऊपर नीचे लिखा हो, कुछ फर्क नहीं पड़ता. तो ABD जो है, आप अगर ABD जो है उसके लिए जो फॉर्मूला लगाएंगे पाइथागोरस को, तो क्या होगा, ABD. इसके लिए होगा AB स्क्वायर प्लस BD स्क्वायर दैट इज इक्वल टू AD स्क्वायर. AD स्क्वायर इज इक्वल टू DB स्क्वायर प्लस AB स्क्वायर, है ना. अच्छा, ठीक है. अच्छा, उसके अलावा बाद में इसका ये दूसरा पाइथागोरस इस ट्राइंगल में अप्लाई करेंगे जो कि प्लेन में है. अच्छा, प्लेन में है तो क्या होगा, DB स्क्वायर इज इक्वल टू DC स्क्वायर प्लस CB स्क्वायर. ओके, लाइक दिस. ठीक है. अच्छा, ये वाली लेंथ हमको पता है, DC स्क्वायर एंड CB स्क्वायर इन दिस triangle, so we can write like this. That means DB, which is the diagonal in the plane, turns out to be in terms of length parameter as 2A square. Diagonal in the lower plane, DB square is nothing but 2A square. Fine, this is still in terms of A, but we need to put this in terms of R. Okay, so what we are doing is, now this DB now is known in terms of A, this AB is as A. Now it is very easy if you apply Pythagoras in this. So DA square is equal to DB square, DA square is equal to DB square plus AB square. So DB square we just found out DB, which is A into root 2, and square of that is 2A square, and AB square is this one. So if you apply this one, then DA square is again 4R square. Okay, so now you know from this and this you get R is equal to this, or you can say A is equal to 4R upon root 3. Very simple, 4R upon root 3. So this one A cube is 4R upon root 3 cube. If we substitute this one, R will cancel out and everything will happen, and then finally the number here will turn out to be 68%. See, the packing efficiency in body centered cube is going to be 68%. Now you see, compare in all these type of units, just simple cubic, then you have cubic close packing or hexagonal cubic packing, or you also call it as face centered cubic, then you get 74%. Here you got 52%. So this has the least efficiency of packing, simple cube, because आपको दिख रहा है यहाँ पे void anyway बहुत ज़्यादा, सेंटर में भी void है, प्लेन में भी void है ना। तो आपका इससे बेटर पैकिंग होगा कि जब आपने सेंटर में एक और एक्स्ट्रा पॉइंट, लेटेस्ट पॉइंट रख दिया है, तो पैकिंग एफिशिएंसी बढ़ जाती है, और इसकी पैकिंग एफिशिएंसी है आपकी यहाँ पे 68%। लेकिन अगर आपने फेस सेंटर्ड इमेजिन किया है, तो जितने ज़्यादा नंबर ऑफ लेटेस्ट पॉइंट पर यूनिट सेल होते हैं, उनकी पैकिंग एफिशिएंसी रिप्रेजेंट होती है ज़्यादा अच्छी। तो यहाँ पे 74% है। डेंसिटी ऑफ अ सॉलिड इज mass per unit volume. So if you have a piece of sample, and let's say if you know its volume, okay, you can measure the volume of this, and it has got certain mass m and volume v, and if you know these two, you can figure out the density. This is a very simple thing. You can even measure the density of a liquid or a gas, anything, because they are dealable at such a big scale. Now we are talking about the density in terms of parameters of unit cell. So how do you go about that? When you say density of a unit cell, I would like to state the formula like this: density of a unit cell is equal to the mass of unit cell divided by volume of the unit cell. Because now we are talking about unit cell, so definitely we have to incorporate everything associated with unit cell. So I am saying density of a unit cell is same as mass of the unit cell divided by volume of the unit cell. So we are the same thing which you knew at a gross level. Now we are talking at a level of unit cell. Fine. What is the mass of a unit cell? Now mass of a unit cell can be represented in terms of the mass of particles it has got, or let's say the lattice motifs, right? For example, if we talk about the simple cubic lattice, simple cubic cell, cubic lattice, and you know that in simple cubic lattice there is only one lattice point per unit cell. So in general, depending upon the type of unit cell, this is for SC. So depending upon type of unit cell, depending upon type of unit cell, there could be n number of lattice points per unit cell. For example, in body centered cube you have 2, for example in FCC you have 4, and in face centered cube you have only 2 again, right? So this number n is a general term here, which is like number of lattice points per unit cell. But lattice point means what? We are talking about the lattice motifs. Points means the points which are occupied by particles, right? So lattice point mean those, and actually I should say here, let's say lattice motif. That will be easier in this definition here. Lattice motif. That means I can say it is either as a molecule or an atom, anything. So for one, let's say SC, you know that there is one lattice point per. So mass of one lattice point here is the representation of the mass of one lattice, one unit cell. In the similar manner, for a different type of unit cell, the mass of, therefore, mass of one unit cell is equal to n into m, where m is now the mass of what it should be, mass of one atom or let's say lattice motif, one lattice motif, which could be either atom or molecule or even ion, anything, whatever you are considering as lattice motif, it could be that. So you have mass of one lattice motif multiplied by total number of lattice motifs per unit cell, that will give you the mass of unit cell. So that's what it means by this parameter. Volume of unit cell is very easy. For example, the volume of unit cell in general, suppose if it is a cube, you know that all the lengths are simply a, length a. Okay, so that means the cube of length. Okay, so volume of unit cell can also be found out. Most of the time in your syllabus you may not have to go with a more complex type of unit cell, but still in general the volume of unit cell can be represented as a into b into c, right? The length parameter which are multiplied together, and the mass is this one, and therefore the density of unit cell will be. And how about this one? How do you get this one, mass of a simple lattice point? You know that you always know atomic or molecular mass number, which is like m, which is atomic or molecular mass divided by Avogadro number. Okay, this is what is going to be m. This is atomic mass or molecular mass. This is your atomic or molecular mass. Okay, if the lattice motif is a molecule, then you have a molecular mass. For example, glucose ke case mein, this will be like a molecular mass for one particle. If it is a metal, then it is single atom lattice motif, so you have atomic mass number. So you divide that by atomic mass number, or molecular mass number is always per mole, right? Per mole. So to find out for one molecule or one particle, you have to divide this mass by Avogadro number, then you get mass per lattice point. And if you substitute here, then you have n into m, where n is nothing but this one. Okay, this one, this number of lattice points here that we have talked about. So in general you can very easily represent, therefore density of unit cell du, density of unit cell is equal to n is the mass number of lattice points per unit cell, nu, so nu into m, nu into m, which m is this one, and divided by volume of unit cell, which is a into b into c. So you see that actually speaking, this is one way to find out the density of a substance, which is like weighing out the mass of a certain volume of the substance, number one. But you can as well talk about the density of the same substance if it is a crystalline substance at a microscopic level, the density of a unit cell. Ideally this density of the crystal density is going to be the same, they are same representation, but here you are able to represent the density in terms of parameters, like very tiny parameters like unit cell length or dimensions, a into b into c. Okay, so this is what is important. So there are simple calculations generally asked. One may ask the question, when we can find out the density by this method, why do we have to worry about that? Well, this is not about just the density. Density can be used to find out some other thing. Please see, the idea is, although the two densities are same here, d is equal to m upon v, this d and this d for the same substance is same, right? But I can use this idea, if I know the density of the substance which is already known to me, I can find out some other parameter which are not possible otherwise. For example, if I am interested in finding out the type of unit cell, which type of unit cell a given representation has from a, there are simple numericals asked based on this. For example, an element, let's say certain element which we do not know, it has a molecular mass. Actually it is called molecular, but it could be atomic mass, because here it is talked about atom element. So let's say atomic mass, this is the atomic mass number. Okay, so n is given to you, which is 2.7 into 10 to power of minus 2 in the unit of kilogram per mole. You can convert in gram per mole, but that's given as kilogram per mole. Fine. And it is like a cubic lattice, because it is said that a cubic unit cell has an age length of 4405 picometer. That means it's a cubic lattice, but which kind of cubic lattice is not clear. whether it is body centered, whether it is face centered, or any kind, or simple also, we don't know. If it is simple, then the number of lattice points should be 1. So we do not know what kind of unit cell is this. It is having a cubic shape, but inside this cubic unit cell, how many lattice points are there per unit cell, that is what is not known. And the age is given, so A is equal to B is equal to C, and that is equal to 405 into 10 to power of minus 12 meter. This is the length of age length of this unit cell, one age length, and it is same as ABC. So definitely we can find out the volume, that should be A cube, okay, in terms of meter cube. We can find out that this can be figured out in the unit of meter cube from this. And the density of the substance is given, which is D 2.7 into 10 to power 3 किलोग्राम पर मीटर क्यूब. सो आपको सब कुछ दिया हुआ है यहाँ पे. आप पूछता है कि व्हाट इज द नेचर ऑफ द क्यूबिक यूनिट सेल. प्लीज, to find out the nature of the unit cell, you should only thing that you need to know is it is definitely cubic, which is given here, but how many lattice points are there, that you have to figure out per unit cell. And you see that this formula relates to that. All you need to find out is n. Okay, in your book that symbol may be Z also, doesn't matter, don't worry about that. But here I know D, which is given as a density of the substance, du is equal to nu into m, and m is nothing but m upon Na, Avogadro number. Okay, this is this one. Avogadro number is 6.02 into 10 to power of 23, and then divided by the volume A cube. Okay, from here. So you have got this one, you have got this one, you have got this one. You can find out this one. From this problem you will get Nu, and from that you will be able to predict which kind of cubic system is this.